Hello, class. This is going to be the final lecture I do for the day. I have been doing some lectures, and each one of these lectures, probably much more so than doing a lecture in person at Wentworth. Take up a lot of time so that I make sure that I'm doing everything and I've got all of my things set up, because there isn't really the class interaction that there is in person at Wentworth. So you have to make sure that at least you have most of the things going correctly. So what I want to look at today is I want to look at centroids of plane areas and line segments. Now, by line segments, I really mean things that are like the same shape as a semicircle, except instead of it being a cross-sectional area of a semicircle, it's just the perimeter, the circumference of that semicircle. And that's what the line segment would be. And of course, the centroid for line segments are much different than centroids for plane areas. And that's what I want to look at first is really, what is centroid. We've sort of covered most of the things in friction that I could have gone with another inclined plane thing, but I think you got the general idea about friction, and there's a lot of other great things that could have been done, but like I say, this is 3 courses in 1 course, so we've already spent a lot of time getting ourselves ready for statics. In fact, we've been doing statics, but now what I want to look at is I want to look at centroids of areas, and I want to look at a couple things. And of course, the definition of the centroid is the centroid of an area, right? I'll just say the x-centroid of an area is going to be or times the total area, right, of the cross section or of the line segment. Let's just talk about cross sections right now, though. So the centroid of the area of the cross section times the total area of the cross section is going to be equal to the integral of x dA, right? And I think it was Newton that first, put this together. And I just want to look at a very simple one first, to just sort of look at what the x-centroid for a rectangle. I mean, this is about as easy as you could possibly get, right? But let's just look at our, let's place a Cartesian coordinate system here. That's my x-axis, that's my y-axis. And we're going to say that this rectangle is going to be h high, which only makes sense. I mean, h sort of stands for height, doesn't it? And then we're going to say that it's going to be b wide. And of course, b standing for base. So I've got this, and what I want to find out is where is the x centroid, right? Where is that centroid? So if I were to look at that, okay, sorry about that. I had to grab, anyway, so what I want to do is I want to find the centroid, and I'm going to look at individual rectangles. I'm going to look at individual rectangles that that are, I'll put it up here, that are dx wide but h high, right? So my cross-sectional area that I'm really talking about, that dA is going to equal h dx, right? And now what I want to do is I want to sum these from 0. Here's where my, axis origin is, right here. So I want to sum those from 0 all the way to b, right? Because this would be h up here, h, and this would be b. So if this is the definition of the centroid, then if I wanted to find the centroid of this rectangle, so let's find x bar of the rectangle, okay? And so that would be the integral from 0 to b of x. And then what is dA? Well, dA, excuse me, is just going to be equal to h dx. I've already done 3 lectures today. h dx, right? Now, if I want to find the centroid times the total area, I could put that there, but I don't. I'm just going to put the total area down here in the denominator, and then I've got everything there, and I basically have my whole equation now for the centroid, the x-centroid of that rectangle. So let's just do some calculus. So 0 to b of x is going to be x squared over 2. So x squared over 2 evaluated between b and 0, right? H is going to come outside, so that's going to be times h, and then over a total, right? Well, if I substitute in b, that would be b squared over 2 minus 0 squared over 2, so that's just b squared over 2, right? So if I draw my thing, I've got b squared over 2 times h times bh. I mean, isn't that what the area of a rectangle is? B times h would be the area of the rectangle. That h, that disappears. One of those b's disappears. So I'm left with the centroid of that rectangle is going to be b over 2, right? b over 2. So the centroid, the x-centroid of that rectangle is going to be right up the middle of the rectangle. Well, what do you know? Of course, we knew that already. We knew that already, didn't we? So a rectangle isn't really a great example. It's an example to show how to do the math, but it might not be a great example to show how we just figured out the centroid. So what I decided instead was I'm going to use a triangle. I'm going to set the triangle up the same way. Here's my x and here's my y-axis. And now I'm going to set the triangle up like this. That's my triangle. Does everyone see that? So I want to find, if I'm using this as my origin, right? And this is my x-axis, that's my y-axis, this is my triangle. I want to find the centroid in the x-axis the exact same way that I did for the rectangle. In fact, let's sort of just cut this rectangle work that we've done out here. And now we're working on the triangle, and I'm just going to give the triangle a little cross-hatching here so that we realize that it is a cross-sectional area that we're working with. And really, what is the centroid of a cross-sectional area? It would be if I took a thin piece of, thin homogeneous piece of plastic, let's say, made as a triangle. Where could I balance? What point in here could I take that thin plexiglass sheet that's a triangle and balance it. I think everybody can see that where we're going to balance, if I had to balance this, wouldn't it be right in the middle? Wouldn't I just balance that on a point right in the middle, and then that plexiglass rectangle would just balance there, right? And so that's what we're really looking at. We're looking at centroids of plane areas right now, and it's important that we do, because we're going to use this later on when we look at the flexure of beams and everything else. We're going to have to figure out what the centroids, what the area moment of inertia is for beams that we're looking at the cross sections for, so that we can see if they can hold up a building or a house or whatever. All right. So this is important to learn too, how to figure out centroids. So so d of a is h at dx. So wait a second, was it? I think that was supposed to be up above there, not down here. There you go. That all works. Excuse me, let me have a sip of water. All right, now what we want to do is we want to work on the triangle instead of the rectangle, because the triangle is going to be a little more difficult, as you can, imagine. Now, when I look at this triangle, I'm going to be looking at a rectangle, right? I'm going to be doing the same thing I did up here. I just want to look at a small rectangle. And I'm going to assume that this rectangle isn't slanted at top because it's so narrow, right? It's so narrow. And how narrow is it? That's right, it's dx narrow. That's how narrow that is. But we've got to come up for an equation for h, right? What would h be at any point along this line? Because we're still going to integrate from 0 to a, aren't we? Excuse me. So what is h going to be? What would be an equation for h? Now, normally I would, ask people in the class about this, but I can't really, because I can't. And it's going to be an equation in terms of x. So as x goes further and further out. Now look at what x equals here, right? When x equals 0, h equals 0. When x equals a, h equals b. When x equals 0, h equals 0, right? That's a pretty easy one. Whatever we multiply it by, it's good. And then the other one is when x equals a, it has to equal b. And so here's what it is. I'm gonna just give it to you, but you're going to immediately see it, right? It's just b over a times x. When x equals 0, then 0 times anything equals 0. And then when x equals a, right? When x equals, that's not a very good, I better put that one sort of inside there and make that x bigger. That's, okay. I don't even know if I could even do it around here. Let's see, there we go. Yes. That parentheses was getting out of control there. There we go. Okay, so h equals b over a. Now when we get out to a, x equals a, it cancels out with the a in the bottom, so h equals b. So you see how that works? That gives us h for the entire thing as we go there. So then what is dA, right? dA is just h times dx, right? dA is just dh times dx, so I've got b over a times x dx. right? So let's go back here to our original equation that we had. If I wanted to find x, the centroid of the triangle, I'm just going to put a triangle down there. Don't think it's a delta, it's a triangle. So if I wanted to find out x, I probably should have made a right triangle of this triangle that I've got over here. Then what I have to do is the same thing. I'm using the same expression that I've got up here. So I'm going to go from, in this case, I'm going from 0 to a, because up here it was 0 to b, but up here it's 0 to a. Could be a little confusing, but it's over the x-axis, so I don't know why it would be confusing. We're figuring out what the x-centroid is for the triangle. So again, let's just write it out, right? X dA divided by the total area of a triangle. And I think everybody knows what the total area of a triangle is, so I don't have to, write that out again. So if I wanted to write all this in, then what I have is I have from 0 to a the integral of b over a, right? B over a. Now x, so I've got, if I'm looking at dA, I've got b over a x dx. So x, I've got to multiply that by dA, right? So that makes this x squared. So I've got b over a x squared times dx. I hope everybody sees that. And then on the bottom, I just have 1/2 AB, because that's what it is for a triangle, right? All right. Now let's sort of look at B and A, and can we get B and A out of there? Sure, that's a constant. We can pull that out. How about x squared dx? That's an A, by the way, not a 0. That'd be x cubed over 3, wouldn't it? So I'm just going to write those out here. So I've got B over A, that comes out. And then I'm going to have x cubed over 3. X cubed over 3 evaluated between A and 0. So that's really going to be A cubed over 3. A cubed over 3. Right? And then on bottom, I'm going to have A, B, and then I'm just going to throw the 2 up on top here, right? So that the whole thing looks good. So the centroid for that triangle that we've got over there, I'll switch it around so it doesn't look like a delta. If I just simplify this equation that I've got over here, I've got B over A cubed over 3. I'm just going to put some parentheses around here. That's a cubed. A times B. And then a 2 up here, right? That's a 2. So can we get rid of a couple A's? Yep, there's a couple A's, and that gets rid of the A cubed on top. We've got a B, so we can get rid of the B's in both places, and those are gone too. So what we have left is 2A over 3. And that would tell us that the centroid would be right about here. Right? The centroid, the x-centroid, would be right about there. So does everybody see how that worked out? 2A over 3, and we worked it all out, and we worked it through the calculus we did here, and that's what we get. And that's how you can find the centroid of an area like that. We can have more complicated expressions, right? Because what if this, instead of being like that, what if it was like this? right? What if we had a parabolic thing? We have that in the book. Look in the book, because I'm going to actually do an example. I don't think in this lecture today, but in the next lecture, I'm going to do an example where I'm using a parabolic. And the parabolic actually is in your book. In fact, I give it to you upside down. I give it to you as a square root. But of course, you can then turn the equation around from the square root into the square backwards, and you can easily figure out where the centroid would be, and the centroid would be down here. Now, what we want to do with this, though, I mean, I'm not done with this example, because we've only found the x centroid, haven't we? Right? So that's the x centroid that we've found. This is not working out well. I think that since we're still working on the same problem, I really did not have to do this. But I'm doing it anyway. Okay, there you go. So that's the x centroid. Now let's, what I want to do is find the y centroid for this right triangle that we've got here. And in fact, we do that the same way, but instead of making our triangles that way, now what we're going to do is we're going to make our triangles, our rectangles. Did I say triangles? We're going to make our rectangles this way, right? And instead of it being dx, it's going to be dy. Does everyone see that? And of course, it's going to, as we go up to this height from 0, now we're going to be integrating from 0 to b, right? We're going to integrate from 0 to b along here, along the y-axis, figuring, this out, because of course, this is just going to be y dA. So the integral y dA divided by the total area still. And of course, the total area of a triangle has not changed, still the same. Yep, I'm going with another color to separate this out. Sorry for you guys that only have black and white monitors, black and white CGA monitors that you're using. I don't know where in the world you would still have those. I don't know, Seychelles. But there you go. Everybody else gets to see that's orange. Yeah, it's quite a bright little page today, isn't it? So anyway, let's get back to this, because we want to find out the y centroid, and we sort of have an idea where that y centroid is going to be, right? The x centroid was way down here at the end, and we're going to find out that the y centroid is right over here too, so that it's got as much area on this side as it's got on that side. I actually didn't do that right. It should have been down further. And in fact, this one probably should be down further too. They should be over here, but whatever, because you know that it's 2/3, 1/3, right? 2/3, 1/3. That's what you've got to remember when you're thinking of the centroid of a triangle. All right. Now, that's what we're going to find here. And so when we come up here now, we're going to find it's only going to be 1/3 of B. That's what I'm supposing, right? I'm hoping that it's going to be 1/3 of B. That's the answer we're looking for. Let's hope that we get there. And we've got plenty of time to do it. So the hardest thing to do with y, y sub c, and we've got that, is to find out the top part. We know the bottom part. So here's what I'm going to do. I'm going to do an integral, and again, from 0 to b this time, not 0 to a. We did 0 to a finding x bar. We're doing 0 to b finding y bar. We're finding this here. This is y bar. That's what we found, and we found x bar in the earlier example. So we're finding y bar right now. So 0 to b going across here, right? And we know that it's got to have y dy in it, because we know that this width here, let's look at what that width is, right? I'm just going to pull out that dy rectangle. So this distance here is dy. what would this distance be? Well, I think everybody can see that down at 0, it is going to be A. So that's our boundary condition. So at 0, at y, I should say y equals 0. That's not very good. At y equals 0, the width is going to equal A. So at y equals 0, what can I call this? I can't call it I'll call it the width equals A. And at y equals B, the width equals 0. Does everyone see that? Now, how would I set that up? We've got two little boundary conditions here that tell us exactly what to do, don't they? Right? So we've got to come up with an equation where at y equals 0, it equals A. So we really want something that would be A minus something, right? Because when anything that's got a y in it equals 0, that's going to equal 0. So now all I need is something with a y in it, right? I need something with a y in it. And what do I need? Let's see, y, when y is 0, A is 0. That's not telling us anything, but when y is B, wait, what? Yeah, when y is B, then x is A. So let's see, y is B. So I've got just the opposite of what I had up in the first part. So I've got my A minus A over B times Y. I'm going to put that in brackets. Let's see if that's right. So at y equals 0, so that's 0, so A minus 0 gives me 0. W, the width, right? The width that we've got here. That's not dA. We're talking about dA here, right? And so dA is going to equal my width times dy. So what is the width here? And we know the width at y equals 0 has got to be equal to A. So A minus that. We know that when y equals B, it's got to equal 0. So when y equals B, then the b's cancel out, don't they? And I have A minus A, and I have 0. Does everyone see how that works out? You know, I just want to point that out to you. I know you're probably thinking, boy, Professor Grinquist's dumb. You know, it's, I looked at it and I saw it in 2 seconds. Maybe not. Maybe you didn't. And that's why I went through it slowly, so that you could sort of see how, you know, the engineer's mind works when he tries to put these things together. Now we've got that, right? That's our integral. And that right there is going to be the width. But we still have y and we still have dy, don't we? So that's a sort of a complicated little thing there. And then on the bottom, what do we have? We've got AB over 2. So that's the easy part. The bottom part's easy. The top part is the harder part. As we start to split these up, right? Because that's what I'm going to do when I find y of that right triangle over there. As I start to split those up, let's just do that, because we can do that with integrals, can't we? When we simplify an integral, it's just going to be A times y. So I've got 0 to b a y, and then I've got minus the integral 0 to b of a over b times y squared. Right? And both of those are dy. I should have put a dy up here. I'm sorry. That's dy, ay, dy, and ab, dy. And then all of those are still going to be over a times b over 2. So I'll put those in later. Let's do this one first. So I can take the a out of here. Then I've got y. That's y squared over 2. So that's going to be b squared over 2. ab squared over 2. ab squared over 2. That's the first one, right? And then minus, and then I've got here 0 to b of y squared. I've got ab, I can take that out of the integral, and I have y squared dy, so that's y cubed over 3, and I've got b, so that's b cubed over 3, so ab cubed over 3b. ab cubed over 3b. I'm writing it out that way because I know I could have simplified it, but I wanted everybody to sort of see, you know, what I was doing there. And again, ab over 2 in the denominator. So what we can do now is we can simplify this. And first of all, we can, get rid of this b here and one of the b's here. So ab squared over 2 minus ab squared over 3. Let's do them in sixes. This is 3ab squared over 6 minus 2ab squared over 6. So this is ab squared over 6. I think everybody sees that. And then we've got ab over 2. So what can we get rid of? We can get rid of the a's. We've got a b and one of the b's, and the b's there are gone. 2 divided by 6 is really just 1/3, so I've got b over 3. What do you know? What we set out to see was correct was actually correct. All right. So I think everybody can see how we've actually worked through the algebra with this triangle here and with the rectangle to begin with, just to sort of get our ideas in order to put this together. And how we would actually figure out centroids of composite bodies and everything else. And we can go up and do things with parabolas or whatever, but those are in the book and they're easy to find. So it's not like I'm gonna, that's what you want to learn is the technique of how to do these. Now what we're going to do in the next lecture is we're going to see how I would use the information we already have of centroids of certain cross sections, and then put those together to figure out centroids of composite bodies. That's what we're doing next. Centroids of composite bodies. And I don't know if we'll have time to look at, well, we will look at the theorems of Pappus and Guldinus, but I don't know if we'll be able to look at those in the next lecture. All right. So that's the end of this lecture, and see you again at the next lecture.